Hello everybody, this is video 8.4. We're going to be talking about prime numbers. I'm going to have to make a real effort to keep this video kind of short because there's not really an awful lot that we need to talk about in terms of prime numbers for this class, but I could go on and on about prime numbers pretty much all day. So there's a lot of interesting stuff we could talk about, but I'm going to have to kind of hold back and not go into too much stuff that's not necessary. So let's get started. Prime numbers. So we should define these terms. A prime number has two distinct factors. Now, distinct is the mathy way of saying that they have to be different. All right. So there have to be two different factors, one and itself. So there's a really common question whether or not one is a prime number. And that word distinct is huge because if we remove that word distinct, if it just has two factors, one in itself, then one would be a prime. It would have one as a factor and itself as a factor. It'd be the same thing. But because they have to be distinct, one is not a prime number because it doesn't have enough factors. Most numbers that are not prime are not prime because they have too many factors. Like 4. 4 is divisible by 1 and itself, but also divisible by 2, so it has an extra factor, so it's no good. 1 is the only case we're going to see where it is not a prime because it doesn't have enough factors. So just keep that in mind. 1 is not a prime number. When we get to factor trees here shortly, you'll see what happens if we let 1 be a prime number and why it really doesn't work mechanically for what we need to do. If it's not a prime number, it's a composite number. So that's what we call any number which is not a prime. We call it a composite. You have to be one or the other. You're either a prime or you're a composite, one or the other. 1 really kind of acts as its own sort of thing, but using this definition, anything that's not a prime, we'll call a composite. It's also important that we define a prime factorization. And what this says is that every counting number is either prime or composite, and it has this unique prime factorization. It can be written as a product of prime numbers, and it's a uniquely determined set of prime numbers. So if we know that 6 is divisible or was divisible by 2 and by 3, so it can be written as the factorization 2 times 3. 6 can't be written as a product of different primes. So 6 can also be 2 times 5. It can also be 3 times 7. 6 is only 2 times 3. It's only those primes. Now, the set part of this, I don't want to go too far into because it's not really applicable entirely to this class. But that set allows us to change the order around and say 2 times 3, 3 times 2, it's the same numbers. So the order doesn't really make a difference. That's why the word set is important to that definition. The order doesn't make a difference. Which primes we're multiplying together, that's what matters. So each number has a unique prime factorization, and each set of primes only multiply to make one number. This may seem more trivial than we even need to express. I mean, it should make sense. If you multiply numbers together, you're not going to get more than one possible answer. So as basic and intuitive and obvious as it may sound, it is important to the whole of mathematics that we sort of define that and make that a rule. Otherwise, we run into some difficulty a little bit further down the road. So it may not seem like an important thing, and for your perspective, you may be entirely correct. But in the grand scheme of mathematics, and that doesn't that sound pretty grand? It makes a huge difference. So I want to talk about this thing called the Sieve of Eratosthenes, and this is an absolutely fantastic activity to do with students when you are introducing prime numbers. And you can see the website where I have generously borrowed this from. And there's about a gazillion different sheets out there like this where you just print it out, photocopy it, and use it with your classes. If not, you can just go to Microsoft Excel and sort of generate one yourself. But this is a really good activity to use. So I'm going to go through the first couple of steps of this. I'm not going to go through the whole thing because it takes a little bit of time. But I'll go through the first levels of this with you. So we have our chart here. I'm gonna do it in green. I like doing green. So the directions here say start at the number 2, put a circle around that number. So I'm going to circle my 2 right here. And then I'm going to cross out all multiples of that number. So I want to mark out the 4, the 6, the 8, the 10. I'm going to be kind of lazy and just kind of squiggle these down, squiggle these down, squiggle these down, here, and here. Now, why are we doing that? Well, we're doing that because we know 2 is a prime, and we can tell 2 is a prime just by the definition. It's divisible by 1 and by 2, so it fits the definition. It's divisible by 1 in itself, so we know it's a prime. Now, we also know that anything that's a multiple of that can't be a prime because that we know all of these numbers are divisible by 1 itself and also 2. Now, it might be divisible by other stuff, like we know this 10 over here is also divisible by 5. But all we need to know that a number is composite is that it's divisible by something other than 1 in itself. And so all of these numbers, because they're multiples of 2, means they also have 2 as a factor. So if we just use the alternate word there, we know they all have 2 as a factor, so we know they're not prime, right? So we've marked out a whole bunch of composites. And it's a nice thing about this activity, like, kids see it and they see 100 numbers and they think, oh my goodness, we've already knocked out 100, 1 being prime, 49 being composite at the first step. So this chart's going to get smaller as we go. I'm going to go to the next number that isn't crossed out. In this case, it's this 3. So I'm going to circle it. I'm going to circle it in red so we can kind of see the distinction here. So we know now 3 is a prime. It's divisible by 1. It's divisible by 3, and we can tell it's not divisible by 2 because it didn't get marked out in the 2 round. So it wasn't marked out in green. So we know that it's not divisible by 2. So now I'm going to cross out the 6, the 9, the 12, the 15, the 18, the 21. And now one of the things that I like about this, when students start crossing these things out, they'll start to notice little patterns here. And so they'll see that these are moving sort of in this diagonal. And the same thing's happening here. And so this gives you an opportunity to talk about divisibility and these patterns and why this pattern works. So there's a lot of interesting mathematics to discuss just within this little pattern here. Now, also, I want to do these in 2 different colors. So the numbers that are marked off in green and in red, that means something. I'll leave that sort of as an open question for you to consider what that means. But there is a difference between the numbers that are marked just in green, just in red, or in red and green. But I'm going to leave that for you. So now we've marked out all of the multiples of 3. We're going to skip the 4 because it got marked out, and we're going to go to the 5. So we'll do this in blue. So I'm going to circle my 5. I know it's a prime. And I'm going to mark off everything that is a multiple of 5. So that's everything here. And then everything here. So these are all my multiples of 5. I didn't really get down there very well. So these are all multiples. And again, the numbers that are crossed off in red and blue, that tells us something. The numbers that are crossed off in green and blue, that tells us something. And even this 30 right here is marked off in green, red, and blue. And that tells us something also. And so again, I'll leave that for you to think about sort of as an extra checkpoint question. We can go on now to, let's see, we'll go purple for the 7. So now we circle the 7 and then cross off everything that's a multiple of 7. And so there's not as nice of a pattern to this, or not as obvious of one. I mean, there is one, but so the 35, the 42, let's see, the 42, the 49, the 56, the 63, the 70. And so the pattern is that this is going to repeat all over again. So the 7 to the 77, the 14 to the 84, the 21 to the 91, the 28 to the 98. So there is a cyclic nature to this, but this is here nor there. We're going to keep repeating this process. We're going to keep doing this until everything is either circled or marked off. And so this 11, this 13, this 17, this 19, this 23, this 29, we're going to start to get our set of prime numbers. And so eventually what's left here, we will have crossed off all the composites and we get left with just the primes. So it's good for students to have a table of primes for what we're going to be working on later on in this chapter. And so you got a choice. You can just give them a table of primes. You can go to Google and type in, table of primes up to 100, up to 1,000, up to whatever. I personally think it's more beneficial that they generate that table of primes. And so if you give them this activity, work them through the first iterations, 2, 3, 5, and then let them try to do the rest. Make sure they use a pencil. My goodness, do this in ink and they make a mistake, the whole thing's ruined. And it's easy to make a mistake. It's really easy to make a mistake, especially when they get to the 7s. You'll get some students, or even the 3s, instead of counting 1, 2, 3 and counting, the 4, 5, and 6, they will count the 5, the 7, and the 9. They'll just count the next 3 spaces that haven't been marked off. And so you want to really watch that students are counting the next 3 spaces, whether they've been marked off or not, which is not an obvious distinction. Anyway, so this is this activity, and it helps us find these primes. So suppose we just want to check one number to see if it's prime or not. And we don't have a prime table. I can't stress enough how useful a prime table is, not just for students, but for yourself. You see a lot of classrooms will have one sort of hanging up in the room for students to use. You got to take it down for tests or whatever, but having it up for conversations or whatever, work that you're doing in class, really, really helpful. If I'm testing a number, I only need to check the primes. If a prime doesn't work, then none of its multiples will keep working. So if 2 doesn't work, I don't need to check 4. I don't need to check 8. I don't need to check 10. None of them are going to work either. If 3 doesn't work, 6 won't and 9 won't. Now, be careful, because some students then think what that means is that if a prime does work, that it won't keep working, or that if a prime does work, that it has to keep working. I mean, the only thing that we need to remember is that if it does work, to keep testing it, because it can work again. It doesn't have to. It might, but it not necessarily. So let's look at an example of like 71. So I'm going to check to see if 71 is prime or not. So I'm going to start with 2. And so I can see 2. This ends in a 1. So I can use my divisibility rule and see this doesn't work. So 2 is not going to work. 3. I can use my test for 3 if I remember it. So 7 plus 1 makes 8. 8's not divisible by 3, so 3 doesn't work. Now, I don't need to check 4. So if 2 didn't work, there's no way 4 is going to work. So I can skip over the 4. I can get to 5. And now 5, let's see, this ends in a 1, so it's not going to be divisible by 5, so 5 is no good. I don't need to check 6. 2 didn't work and 3 didn't work, so there's no way 6 is going to work. I can get to 7, so I can see 7 goes in 10 times with 1 left over. So there's a remainder, so that's not going to work. I don't need to check 8 because 2 didn't work. I don't need to check 9 because 3 didn't work. I don't need to check 10 because 2 and 5 didn't work, so 10 can't work. So I'll check 11. And so now 11 would go into here 6 times with 5 left over. And now this is important, because once your quotient gets smaller than your remainder, then what that means is you've checked everything that could possibly work. Now, I'm not going to go into the reasoning behind this, and we could also say that we could check up to the square root, and we know the square root here is going to be it's going to be 8 and change. So once we get past the 8, it's not going to work. If you want to know why that's the case, certainly talk to me after class or in office hours, and I'll explain why that's the case. But this just lets us know, and this stopping point is a lot sooner than you might think. We don't need to go all the way up to 71. So if you feel comfortable talking about the square root, if you've talked about square roots already, you can introduce that. Or you can just use this idea of when the quotient gets smaller than the remainder, then we know we can stop. It's the same idea, um, but this lets us know when to stop. So if I want to check 71 as a prime, you might think we got to check 71 numbers. In reality, we only have to check 4. We only got to check 4 primes. The fifth one lets us know that we've gone too far. So I mean, the fifth one's there. But really, if none of the first 4 work, then the fifth one's not going to work either. So it's not checking as many numbers as you might think. It's a much quicker process than it probably appears. The last quick thing I want to talk about is about factor trees. You've probably seen these before at some point. This is going to be really helpful in the next section. What we're going to do is we're going to take a number, say 36, and I want to factor it into 2 numbers. So I just want to find 2 numbers that multiply to make 36. Now, there's nothing that says you have to use 2 numbers, but this is typically the way that we do it in classes. You could do this as a product of 3 numbers or 4 numbers if you're just feeling that ambitious. But typically, we just do this in terms of 2 numbers. So we'll do 3 times 12. And now what I like to do is when I get to a prime number, when I recognize that I've got a prime, I like to circle it. And I'll explain the reason why here in a moment. Now, this 12 is not a prime, so it factors again. So there's 4 times 3. So again, I'll circle that 3. And then this 4 factors into 2 and 2, and those are both prime, so I will circle those. So now I've got 36 as the product of 2 times 2 times 3 times 3. Now, an alternative to circling these, you'll see in some books, or you'll see some people when they do these, they will carry down that 3. So this is 4 times 3, and this is 2, 2, 3, and 3. So each level shows this as a product. Either way works. The idea behind circling it is that we don't lose anything. If I don't circle this 3 or this 3, it's easy to forget that they're there. And so if I don't circle, this 3 up here, I could just look and see 2, 2, 3, and so I don't, I just get the 12 and not the full 36. So circling helps us to not lose any prime factors. Carrying them down like this does the same thing. It helps us remember all these prime factors. But we're going to keep going until we get this just down to primes. Now, I mentioned earlier that 1 can't be a prime. And so if we were to allow 1 to be a prime, then I could take this 2 and factor it into 2 times 1. And then that 2 factors into 2 times 1. And that's 2 times 1 and 2 times 1. These factor trees would never end. So preventing 1 from being a prime, it follows the definition. But if we allowed 1 to be a prime, you see these factor trees kind of wouldn't work. At least not the way that we want them to. So this allows us to find these prime factorizations. And again, this is unique. If you have another student who, instead of starting with 3 and 12, starts with, say, 9 and 4. So they're going to get 3 and 3, 2 and 2. And so notice that as a set, right? So if we just ignore order altogether, they get the same set of primes. They still get 2 and 2, 3 and 3. If you are so inclined, you could write this using exponents, 2 squared, 3 squared. But they get the same thing. And so this uniqueness means that we can start whichever way we want as long as we're using a correct factorization. But no matter how we start, somebody else could start 2 times 18, and they're still going to get 2 squared times 3 squared. We're going to get the same thing. And then conversely, if we start with this prime factorization, 2 squared times 3 squared, it can only give us 36. That's all we're going to get for that. So your checkpoint, I want you to try to find the prime factorization of 1350. So you can use the factor tree that we just talked about in the previous slide. You can do it sort of by trial and error. You may need a prime table to make sure that you're picking primes. But we're going to need this process for the next section. So this is all sort of building on itself. The divisibility rules, so we can check for primes. And now we can identify primes and find prime factorizations. We're going to apply that in this next section to find greatest common factors and least common multiples. So if you have any questions about anything, please let me know. Thanks.